Ethers are generally pretty stable, but one reaction they can undergo is acid-promoted cleavage. So we're talking about reactions with either HI or HBr, which are strong acids. So we'll give some examples. And something like diethyl ether, when treated with excess HI or HBr, would give 2 equivalents of alkyl iodide, in this case both ethyl iodide, and also water. And if we had slightly different ether, let's say methyl terbutyl ether, and we treated it with the same reagents, we would get 2 different alkyl halides, now terbutyl iodide and methyl iodide and water. And let's see, if we have a aromatic ring attached to the oxygen, then the products are actually a little bit different because we cannot undergo cleavage at this carbon-oxygen bond. So if we draw the products, right, so this is sort of X, we can't do that. So we get phenol, and in this case, methyl iodide. And then one more example, let's look at if we had diphenyl ether. Under the same conditions, there would be no reaction. Okay, so what is required and what's happening here? We are doing substitution reactions at all of these carbon-oxygen bonds. And notice that this carbon is sp3, and this carbon is sp3, and that works really well for this type of cleavage reaction. This carbon is also sp3, and so we can cleave both carbon-oxygen bonds one at a time. This carbon is sp3, so we were able to cleave here, right? But since this one is sp2, that means we cannot cleave this bond. So again, X. And again, we cannot cleave these bonds because these carbons are sp2, and we cannot do substitution reactions on sp2 hybridized carbons. The mechanism for the substitution reaction may be Sn2 and also might be Sn1. In order to figure out what the mechanism will be, you have to look at the alpha carbon and see how sterically hindered it is. So talking about the carbons next to the oxygen, if they are primary and not sterically hindered, or methyl, those will all be Sn2 mechanisms. And then if it's tertiary, like over here, right, then this will undergo Sn1. So we need to have that in mind if we're going to draw an appropriate mechanism for the cleavage here. This again would be Sn2, and then those don't undergo substitution. So let's look at an example. So let's give the terbutyl, let's see, ethyl, for example. And we'll treat this, again, it could be HI or HBr. Why don't we use HBr in our example, since we used HI on the previous page. And the products would be terbutyl bromide, ethyl bromide, and water. Okay, so the first step in the mechanism, if you're treating something with a strong acid, will be protonation. So HBr is a strong acid, and so we'll do a proton transfer, and the oxygen will pick up that proton. And we'll draw in some bromide as well. Just ignore that line. Okay, so now that we've protonated this, we've potentially created a good leaving group for breaking one of those carbon-oxygen bonds. And when you have potential Sn1 and Sn2 mechanisms that occur, and remember we talked about at the unsubstituted alpha carbons, the mechanism will be Sn2 for cleaving that bond, and over here Sn1. So the Sn1 mechanism will occur with a faster rate. So we'll go ahead and draw that one occurring first. So we said loss of a leaving group, right? And we lose this alcohol as a leaving group, will generate a stable carbocation. And then we know that alcohols, since they're neutral, are good leaving groups. So draw our tertiary carbocation, and then we also produced some ethanol. And bromide is around, a good nucleophile, so we can definitely do a nucleophilic attack here. So that produces the first product, which is our tert-butyl bromide. Okay, but then the alcohol, ethanol, will continue to react, right? I forgot to mention excess HBr will be required because we're going to do the same type of mechanism. So with more HBr around, that oxygen of the alcohol can pick up a proton. So we'll draw out the protonated alcohol and some bromide, which formed in that step. And then because the alpha carbon here is unhindered, it's definitely not going to do loss of a leaving group because we never form methyl or primary carbocation. So instead this reaction will go Sn2 because of the unhindered carbon. So then we see how we get some ethyl bromide and also water in the end. So this example was a good example mechanism because we had both Sn1 occurring and followed by Sn2, and again that's because in one side the alpha carbon is tertiary, so it will prefer an Sn1 mechanism, and then the other side is primary, so it will prefer Sn2. And remember, when you have both, Sn1 will occur with a faster rate, so we draw that one first.